it has for a sharding spec. And I will add disclaimers that the finer details are a work in progress. And there are, like as we go through the spec, we'll point out some kind of particular details that are still, in some ways at least, either partial question marks or where there's several options that we're trying to choose between. So I guess I'll start off with the motivation. So first of all, the things that we figured out over the last over the last month or two are, number one, the newer roadmap is starting to fairly heavily use aggregate signatures. And aggregate signatures basically allow you to have a signature that that combines together as signatures from some set of validators, and the cost of verifying a signature from a very large number of validators is basically a constant size and constant time plus a very small increment of both size and time for each participant, right? So for like the initial signature by itself takes something like 96 bytes and it's one elliptic curve pairing, so it's somewhere in the tens of milliseconds. And adding one participant adds 1 bit and adds 1 elliptic curve addition. And an elliptic curve addition is like 1 over several thousand of a pairing. So what this means is that you can basically get a signature that contains an entire committee, and the signature that contains an entire committee is only going to be a few times more expensive than a signature was before, right? And there's several different ways to do this. So one is BLS signatures, and there's ETH research posts about that. Another is that you can, if you want something purely hash-based, then you can do Starks on top of Lamport signatures, and that's that's a likely more longer-term sort of roadmap. And like aside from those two, there's theoretically other options as well, right? So what this gives us is it basically gives us it reduces the marginal cost of having more validators. And so maybe by a factor of something like 100, right? So what that means is that we can have more validators and the whole thing can be more efficient, and we can knock the minimum validator size down from 1500 ETH to 32 ETH along with a bunch of other good stuff. The second thing is that a lot of the kind of overhead and math involved in dealing with these signatures and processing large numbers of validators basically involves kind of shuffling bit fields around and like doing a bunch of like ORs, XORs, whatever into big bit fields. And it involves a lot of like integer manipulations all over the place. And so this is the sort of thing that you can do really, really fast if you optimize, build an implementation in C++ or whatever, or even if you build an implementation in Python and just use XOR a bunch or use bit operations a bunch. But it's not the sort of thing that's particularly fast in the EVM, right? So basically, there's a bunch of factors together with the facts that we've made more and more progress on looking at what full proof of stake would actually look like that basically drive a decision toward not going with this roadmap of building layer 2 proof of stake on top of the existing chain, but instead having this structure where basically you have a proof of work main chain and you have a proof of stake chain that kind of piggybacks on top of the proof of work chain. And this proof of stake chain, theoretically the design that we have could totally function as a kind of non-scalable full proof of stake system, right? But it's fairly easy to like basically dual purpose a lot of the messages as also being attestations for blocks inside of shards, and so we get a bunch of shards for free. And how many shards do we get? Well, because we can now use aggregate signatures, we get even more shards.
Right, so I think the number of shards that we're looking at kind of as a maximum right now, if everyone is a validator, is around 4,000 shards. Mm-hmm. But maybe as a more approachable target, we'd start off with something like 100 shards.
Right. So I guess that like one of the challenges here, right, is that you at first I think we kind of thought that like naively that the number of shards could go up or down. but that's actually a pretty bad idea, because what that means is that if I have a contract on shard number 573 and then a bunch of people drop out, and then my shard like pauses for 5 years or whatever. So the approach that, this is one of those not fully decided things, but the approach I'm favoring is where we set a number of shards, and the number of shards is high, so at 4,096. But then the idea is that as the number of validators participating in proof of stake goes down, then the gas limit of the shard, so it basically drops a lower than what the maximum value would be. Right? So if, for example, the gas limit of a shard, if literally everyone was validating, would be like 20 million, then if only 10% of people are validating, the gas limit of a shard goes down to 2 million. And because you have 1/10 as many validators, each validator would on average be responsible for 10 times as many shards, but each shard has 1/10 the capacity, so it balances out, right? So it's 4,000 shards, but in expectation, maybe 400 shards worth of capacity. But once again, not set in stone, this is like one possible model.
In terms of other innovations that we have that are quite recent, I guess one is that we're thinking of changing the random beacon. So instead of using a pure random, which is potentially prone to some manipulation, we can use random as a way to seed some initial entropy for what's called a verifiable delay function, a VDF, and then use the VDF as a way to generate random numbers over time in such a way that you can't predict what the random numbers will be at the point where the seed is being determined. And so that will allow us, in particular, to have a very stable heartbeat and random number generator from which the shards can build upon, which will lead to really, really low variance blocks. Another kind of innovation at the shard layer is the idea of cryptoeconomic proofs of custody. So a lot of sharding is predicated around the idea of validators voting on the availability of blocks. And what we have had in the past as the main assumption is an honesty assumption that, let's say, two-thirds of the network is honest when they make their vote. And so if we sample them in committees of fixed size, then with high probability, the outcome of the vote will reflect reality. But I guess we've managed to strengthen that with cryptoeconomic proofs of custody, and basically the idea is that when you make a vote, you have two options. You have, you can either make a 0 vote or a 1 vote, and this 1 bit of flexibility is going to be your custody bit. And the custody bit, as a validator, is a bit that you can only compute if 1, you have custody of the data, and 2, you have custody of a secret, which only you know, and that provides some of the cryptoeconomic incentives to make the whole scheme work. So if for some reason you don't have the data, then it's really not to your advantage to make a vote, because in the future you'll have to reveal your secret, and if the bit you chose at random, like a coin toss, then you'll just lose your whole deposit. So in terms of kind of at a very high level, we have kind of 3 components. We have the main chain, and the main chain is pretty much used for only one thing, which is to seed the deposits. So validators make a 32 ETH deposit, and there's some initial, like some initialization that goes there. For example, initializing your RANDAO commitment, and also some technicality regarding BLS signatures. And then once you've made your deposit, you're a validator. And you're a validator for everything. You're a validator as a Casper validator, as a beacon chain proposer, an attester, as a shard proposer, as a shard attester, and also as a notary. And so you'll be called upon on a randomized basis to perform all these tasks. And like one of the designs we're considering basically is similar at the beacon chain level and at the shards, where you have predominantly two types of participants. You have the proposers who will extend the chains, and then you have the attesters, which you can think as kind of co-proposers, which together with the proposer will attest to the fact that the proposal is building on the root, on the tip. So that creates basically friction for what traditionally is a monopoly proposer who can just propose wherever he wants. Now you kind of need to propose as a group. And then you have infrastructure which is the glue between the shards and the beacon chain, and these are the notaries. So the function of notaries is basically to go in the shards and vouch for the fact that some checkpoint, all the data between some checkpoint and the previous checkpoint is available. And then once there's a quorum which is reached on this checkpoint, the votes are put into the beacon chain, and then the Casper finality loop can be run on the beacon chain. And so what that creates is basically cross-links between the shards, which allows for cross-shard communication. So basically every shard is given live client access to every other shard, and communication can happen via Merkle paths to the roots, to the checkpoints.
Yeah, I have a question on the proposers.
Mm-hmm.
Yeah, a quick question on the proposers. So previously, when the proposer was alone to decide what they could do, they could also optimize differently the way that they propose blocks, whereas in the group, everybody has to propose the blocks the same way. Is that the idea?
What do you mean by a way? Like, what's an example of an optimization a proposer could make?
It might give preferential treatment to a customer of theirs.
I see. No. So the attesters would not be kind of policing to make sure that the proposer followed a fair gas policy or anything like that. The attester would just be attesting to a few things. One is that the proposer actually built a block on the head. Two is that the block is valid, and three is that the block is available.
Mm-hmm. So the proposer still has monopoly on choosing which transactions will go in the block, but he doesn't have monopoly on where the block is being built upon in the chain. And he also can't do bad stuff like building unavailable blocks or invalid blocks.
Yeah. And I suppose you could consider doing like crazy stuff like having the attesters be less likely to confirm a block if it censors transactions, but like, there's a whole bunch of risks about that, and that's something we haven't even started studying. So in terms of like stuff that I've written down here, this and this is basically the kind of approximate simple proof of custody algorithm. So the general way proof of custody works is that you're attesting to, when you're attesting to a block, you're attesting to a block header, and you can think of a block header in very simplified form as just as being a Merkle root, and the Merkle root has a bunch of underlying data, and your proof of custody is basically taking the underlying data, then XORing in some particular seed into every leaf, and then you calculate the root of that, and then you take the first bit of that. And the idea is that someone can submit this proof of custody, then later on, other people can challenge, and they can basically, like, the idea would be that at some point in time, you would be required to reveal what your seed is, and once you do that, then other people can discover what your committed bit should have been. And if they discover that the bit you committed to and the bit they calculated are different, then they can play this game where they basically challenge you on particular indices and you're required to respond with Merkle branches. And after log-n steps, they can kind of zero in on the specific place where you calculated your proof of custody wrong, at which point you get slashed and they get a bounty for catching you.
And one thing to mention is we could have made the custody bit longer, so it could be like a full hash. But the reason why one bit is kind of optimal is from the point of view of BLS aggregation. So when the validators are called upon in a committee, either in the form of an attestation committee or in the form of a notarization committee, they will be voting on the same message. So they'll be signing the same message. And it turns out that with BLS aggregation of signatures, the verification cost is linear in the number of underlying messages, of distinct messages that are being signed. So in our case, we only have 2 possible messages because there's only 0 or 1 in the first bit.
Another thing to add is that there is also an information theoretic argument, which is that if every distinct validator provides their own distinct proof of custody, then the amount of information you'd have to throw onto the chain is basically 32 bytes times the number of validators. Whereas here, the information we're throwing on is basically 2 bits times the number of validators. And yes, like technically it can be 1.53 bits or whatever the number is, but like it's extremely small, right? So this is part of why we can say that you can have a signature that represents an entire committee, which doesn't take that much longer to evaluate than a traditional signature would. Yes?
Is the proof of custody for the state of...
Is this proof of custody for the state of the beacon chain or the state of the shard chains, or?
The proof of custody is for verifying data availability of shard blocks that are being attested to in crosslinks. And like this is a bit of a simplified diagram because like when you're attesting to a crosslink, you're attesting to not just one block but an entire chain of blocks going back since the previous crosslink. But like there are different ways to do that, right? Like you can have like some kind of more advanced, like weirder Merkle structure here. You could potentially come up with some like block tree structure where that more naturally turns it into some kind of Merkle tree. Like there are solutions. Yeah.
So I guess one thing which might be worth pointing out or listing is all the services that the beacon chain does. So you can think of it as a kind of the system chain or the manager chain. It does all the kind of nitty-gritty stuff that manages all the shards. The shards themselves are extremely clean. They're mostly just data. So just a word on that. In terms of roadmap, we have phase 1 of Ethereum 2.0, which is transparent sharding. But the sharding part is only really solving the data availability challenge. So coming to consensus as to what data is being pumped into the shards. And then phase 2 plus is basically the EVM 2.0. It's adding an EVM with a notion of state or a notion of transaction. And so in terms of the various services that the beacon chain provides, number 1 is the heartbeat and the random number generator. So we have this global clock assumption that all the validators know what time it is right now. And then every 5 seconds, there's a random number which is output, kind of constructed, and we can talk about that, how it's constructed later. And for every random number, you have 1 heartbeat. Another service that the beacon chain provides is all the accounting for the rewards and penalties and deposits of the validators. So every time an action that is incentivized should be accounted for, that's done in the beacon chain. And that includes, for example, the slashing conditions when bad things happen. Another thing is that the beacon chain is where all the Casper votes get aggregated and counted. So, like the design that we're considering really nicely couples sharding and Casper. So, in terms of reused infrastructure, every shard is where the individual votes are made, and so we're reusing messages, we're reusing gossip channels, and we're also reusing the aggregation that each individual shard has. And then we have these very small and efficient to verify messages, which are then put into the beacon chain. So you can think of every shard kind of as a staking pool in and of itself. Each shard having, for example, 1,000 validators. And so that's part of the reason why we have so much efficiency. It's basically the design is as if we had one participant per shard, but actually each shard has 1,000 participants. And then, yeah, the final service which I talked about is the crosslinks, which allows for cross-shard communication.
You mentioned that in phase 0 or 1, there would be data accumulated about, or in the shards that there would be attesting to, but there would be no VM. What is this data that's accumulating?
Decentralized Twitter messages.
Can you give me a little bit deeper example about how that would work?
No, like basically until there's a VM where you can run like real dApps on top of it, you basically have two options, right? One of them is that you use the blockchain as a kind of high cost but very high availability data store, and the other one is that you basically come up with a custom execution engine, and you basically have some application where you sort of agree off-chain that some particular function calculated of the entire chain is something that you care about. And then that could be, that would make sense for a lot of non-financial applications. And then if you want to actually calculate it, you could end up, using some cryptoeconomic execution, like zero-knowledge succinct proofs or whatever.
So I think the most simple and compelling example of a alternative execution engine is actually TrueBit. So on TrueBit, you can agree on a program, agree on an input, and then somehow with some magic, very cheaply, also agree on the output. The problem is that agreeing on the input and on the program to run is very expensive because that could be megabytes or more. And so traditionally there's been this problem in how do we agree on the inputs, because if they're not available, then the verifiers can't do their job properly. And so one very compelling use case for sharding before phase 2 is as a file storage layer for TrueBit. So you'll be able to put tens or hundreds of megabytes of input data and programs, and then some other blockchain, the legacy chain or even some other blockchain, can have a light client access to these shards and say, hey, this data is available because it's in the shards, and you only point to it with a single hash.
Yeah.
So as far as I understand, each epoch, the validators will be asked might be asked to validate different shards, right? So what I'm thinking about is that if I'm a validator and I've been validating shard number 3, and now I'm going to start to validate shard number 5, I have to somehow find my future peers ahead of time. And those other peers have to find me, so the network has to completely reform between the epochs. Did you think about how this is going to be done?
So I guess first of all, there are going to be a lot of static peers that just stay on the same shard, right? Like users probably will be. There's going to be nodes that just run on every shard. Also, our current spec has shards having long-term proposers that stay on that shard for a period of something like a month or more. So, the network, it's definitely not the case that literally the entire network forms from scratch, but it definitely is the case that there will be a high amount of churn. As far as handling churn, the one thing that we can offer as a mitigation so far is that you can know where you'll be allocated to some amount of time, like plus a few minutes in advance. So, like basically, you'll have more time to switch shards than, like substantially more time to switch shards than it normally takes like a get or parity node today to like switch on and connect to the network. But like, we welcome like feedback and thoughts on like peer-to-peer network designs that kind of optimize this more, because it is something that people have started thinking about.
So in terms of how many shards each validator is assigned at any given point in time, we're thinking exactly 2. So 1.
Well, you're thinking exactly 2. I'm thinking 1 plus 1, 2 divided by the percentage of validator staking, whatever. Yeah.
Approximately 2.
Yeah, I guess like if a shard has a 10th the maximum gas limit, it's really only 0.1 of a shard.
So 1 as a proposer, and you're assigned to the shard for a fairly long period of time, and part of the reason is that if you want to make good proposals as a proposer, you need to have knowledge of the state so that you can prioritize transactions for gas and stuff like that. On the other hand, when you're assigned to a shard as a notary, the shuffling happens much faster, so it happens every 10 minutes. It's okay to shuffle very fast because the main thing that the notary has to do is download data and sign off when the data is downloaded. And the only data that it has to download is from the very recent past.
Okay, so I just want to preface that I'm very early to understanding the concepts here. But the one thing that I wanted to understand is that basically you elect what crosslink is going to happen next every 5 seconds, or how does that work? I just want to know how the crosslinks go back into the beacon.
Yeah, so there is, and this is partially question mark territory, but generally with every new slot, so with every new period of 5 seconds, it becomes possible for a set of validators to vote on a new crosslink on some particular shard. Though the specific set of validators and the specific shard they'll be going on will be picked a few minutes in advance. Probably like 1 to 2 epochs in advance, and you do need that to be the case because for them to be able to vote on the crosslink, they need to have enough time to be able to validate the portion of that shard chain since the previous crosslink. Denny.
So just to be clear, the requirements of a validator would be to have the beacon chain, run the beacon chain, be able to run 1 to 2-ish shards, also sync to the main chain because the main chain refs likely for finalization.
Right.
So that's the system requirements?
Yes. Technically, if you want to be lazy, you can be a light client for the main chain and a full client for the beacon chain. Like that's your choice.
Could you clarify a little bit about the phases, phase 1 versus phase 2? Are they more research milestones to be completed, or is it the intention?
They do, yeah. So they do represent milestones of like what becomes possible in terms of capability. So like roughly, it's phase 1 is basically the beacon chain with the shards acting as data shards. Possibly phase 0 or phase 1 minus epsilon or whatever you would call it is just the beacon chain as a proof of stake chain without shards. Phase 2 is the shards with computation, and then later phases like basically bring in cross shard communication and like more levels of functionality, and then eventually kind of like bringing in the existing main chain into the shard, into the sharding system, like possibly as something running on one of the shards.
Okay. My question is, is that roadmap intended as research milestones, or is it actually production deployment, you know, like this will go live, first phase 1 goes live without any execution engine, or is it possible that the execution engine would be developed, you know, in parallel as an architectural layer so that phase 1 and phase 2 go live at the same time?
And that's possible too, though, I mean, realistically, phase 2 would happen after phase 1 because, like, phase 2 is something that would need to be, well, I mean, it is, okay, fine, it is theoretically possible that so much progress will have been made on phase 2 that we could go live at the same time. And also there's, like, another dimension is, I guess, the level of maturity of the sharding clients in general, because I feel like there is obviously a question of, you know, like, is phase 1 with no data, data and no execution going to go live as a quote mainnet with like people staking real ether on it? And I mean, like, my personal opinion is that if all of the different sharding clients like Prismatics, Nimbus, Pegasus, and so forth were stable and had like good, like well-tested and audited versions of phase 1, then sure. But if the level of the clients themselves has low maturity during phase 1, then phase 1 should obviously be just a test bed, and then once it gets to a kind of higher levels of stability, then it might be phase 2 that starts being a mainnet. Like, I'm not really married to any path.
I mean, phase 2 has a lot of challenges to solve. So it's about setting the right foundations for the EVM. And so what we know so far is we probably want WebAssembly. We also probably want storage rent, and that's something we haven't really figured out yet.
We may want different execution models that facilitate sharing witnesses across transactions, possibly, and friendliness toward various privacy zero-knowledge schemes, which is kind of the same as custom witnesses.
And also, we might want to favor asynchronous, for example, cross-contract communication.
But like, if a really cool synchronous scheme gets discovered, then like totally, yeah.
Yeah, and we also need to figure out account abstraction.
How many checkpoints do you think that we have?
How many checkpoints we will have? How many blocks will be notarized? It will be one block every 10 blocks, or one block, every block will be notarized?
What do you mean by notarized? Oh, you mean like the Casper FFG cycle? Yeah. So, like, somewhat of a question mark. The number that's in my head is like 1 swat every 5 seconds, and 100 swats is an epoch. So 500 seconds an epoch, and so, you know, like, average time to finality 1,000 seconds, though there are ways to optimistically reduce that to 500 potentially, but we can talk about that later.
Could you please detail more the crosslinks, how it works?
Sure, I'll draw a diagram. Bye-bye, Randall. Here,
Okay, crosslinks. So basically, once every epoch, you have a new committee of notaries which are assigned to this epoch, and they're all going to vote on some checkpoint in the shard. And the checkpoint is basically an epoch boundary. One of the things that I mentioned before is that we're merging the act of making a Casper FFG vote with the act of voting on the checkpoint. So it's one single message with a single signature, with a single aggregation scheme and a single gossip scheme. And then once you have this aggregated message, the beacon chain proposer is going to be incentivized to take it and to include it into the beacon chain. Once the Casper finality loop has run over this beacon chain block, which contains the checkpoint, then the shard becomes finalized.
So here's my here's my drawing of the dependency graph. So the thing in the middle is the beacon chain, and like don't imagine this as two shards chains surrounding it. Think of this as being kind of like the middle of a hollow cylinder, and imagine the shard chains as being like the edge of the hollow cylinder, and imagine like 100 or 1,000 of them surrounding the beacon chain. So the beacon chain is clearly a chain, and the shard chains are clearly chains. And you notice there's two kinds of links that are going between them, right? So one kind of link is that there's a link going where shard blocks depend on beacon blocks. And this happens kind of implicitly because it's the beacon chain that controls the randomness, and it's the randomness that determines which validators are allowed to create and attest the blocks on particular shard chains at particular times, right? The second kind of link over here is the link where the beacon chain can become dependent on a block in the shard chain. Now, because the shard chain by its, individual shard chain blocks could always screw up, and the beacon chain by itself has no ability to fully validate all blocks on all shards because there's way too much data. So in order for the beacon chain block to become dependent on a shard chain block, it basically has to go through the structure where there is a committee and the committee votes on it, and once the committee votes on it and the votes all get included, then this forges a kind of dependency link where, basically from the point of view of this fork choice, this is now recognized as the leading shard block, and if these shard blocks are invalid, then this beacon block and all of its children are invalid as well. Now sometimes crosslinks can get kind of partially included at first, and then their inclusion gets finished later. And that might happen because, let's say for example, this proposer is somewhat faulty and just had really terrible network connectivity, only saw a quarter of the crosslinks, and then of the crosslink messages, and a bunch of other crosslink messages made it easier. So then over here, this is viewed as having a crosslink, this is viewed as having a dependency on this. So basically think of it as as a sort of a kind of structured dig where you have chains and you have these interconnections between chains, except interconnections that make the center dependent on an edge are more sensitive, and so they require this confirmation structure to become binding.
So one of the things we're looking into right now is how can we maximally decouple the beacon chain from the shards. So if the beacon chain is kind of locally forkful or a little bit faulty, we still want the shards to power on. So I guess at a minimum, you want the shards to respect the finalized checkpoints because it's finalized. And so we're considering having only this dependency in this direction. In this arrow. So this arrow will only point towards finalized blocks. In terms of bringing crosslinks in, the crosslinks don't have to be put in at any specific height, or there may be some constraints, but there's also lots of optionality.
So I have a question about scaling, right? That I think in Taipei there were still just 100 shards, and now there's going to be a whole bunch of them more. And there's this maxim that the amount of traffic will grow to the capacity, right? So we can expect that each and every shard will have about as much traffic as, say, the main chain today, right? And what's the thinking here in practical terms for processing power of the various players in the system, with so many shards around there, right?
Sure. So, almost all actors in the ecosystem, and definitely all actors in consensus, basically only need to have process three things, right? They need to process the beacon chain, then they need to maintain light client access to the shards, But like technically they don't even have to do that because the beacon chain maintains like client access to the shards. And they need to maintain full client validation on the tiny subset of shards that they're assigned to, which we can say is 2, because if it's going to be 20, then it'll be 20 shards operating at 1/10 capacity. Right?
Sorry, I didn't understand what you mean by beacon chain providing access to large clients.
Basically, the idea is that the beacon chain state contains the crosslinks to the most recent crosslink that was published for some shard, right? And so what that means is that the beacon chain contains a recent state root of the shard. And so the beacon chain is a light client of every shard. Yeah. So, yeah, so like basically in terms of the load, right? Like the goal is that running the beacon chain should take like maximum, you know, like half the whatever acceptable computation load is, and then like so like C over 2, and then this over here would take another C over 2. And that's basically what the load of a node would be. So, and the load over here is proportional to the number of nodes and to the number of shards. And well, the capacity of the shards is proportional to the total capacity of the shards proportional to the number of nodes. So it's kind of the same thing. So in total, you do get this kind of like of like basically something like C squared over 2 capacity. But like every node in consensus, my personal goal is closer to the overhead of a Bitcoin node than the overhead of a present day Ethereum node, and I think we can get closer and closer to that over time. Though I will add that, you know, like block explorers and exchanges and so forth may want to run full nodes for more shards, and like in the case of block explorers, all shards, and you know, like yes, that will be more expensive for them.
So when a notary is expecting to relocate to a new shard, they will, as you said, that they will be required to download the current state, right?
Not a notary. When a proposer is relocated, yes, they will. So proposers get relocated slowly, and so they get a lot of time to download the state. But notaries do not need the state.
But I thought the notaries do need the state to verify what the proposers are doing, no?
Notaries can statelessly verify.
Oh, okay. Because I was going to suggest that instead of basically everything happens on a certain, for everybody at a certain time, you can actually sort of do it gradually. You just drop one person or a committee on one shard and add another gradually. So there's no like a huge network traffic spikes at the borders.
Yeah.
I mean, one of the ultimate end games of the design is to be quantum secure, and 2 places where we would not be quantum secure, potentially at launch, is number 1, BLS signatures, and so the roadmap there is to replace them with stocks, which kind of have similar properties, and then the VDF for the random beacon potentially would also be not quantum secure to start with, but with a roadmap to upgrade it, also potentially using stocks.
Yeah, like basically all of the primitives we're using have a purely hash-based alternative if/when it's needed / we're ready to upgrade to it. But like there are also kind of more performance versions that work given the technical constraints that we have now. Yeah.
Back to crosslinks, could you detail how a call between 2 contracts will happen? 2 contracts on different shards, obviously.
So basically that would, I mean, the main approach that we have for that is an asynchronous call. So basically the idea is that step 1, you would have, say, a function call happen over here, and this would like create a receipt. Then step 2, this you would wait for this to get cross-linked. Then step 3 over here, the shard chain over here would be aware of the beacon chain here, therefore aware of this, and therefore aware of this, therefore aware of the crosslink. And so at this point, you would be able to send a second transaction, which basically takes that proof plus a record that that crosslink, that particular receipt wasn't consumed yet, and then does whatever the credit operation is on the other side.
And then we need the results. So I'm not costing to get the results. If it's a call,
Oh, if it's a call and you want an answer, then yeah, you pretty much have to like do a 1-2.
so I need two costings.
Yes. Now, this is if you want to kind of rely on the base chain, right? Like there is also this crypto-economic alternative where basically a shard over here just accepts that, or yeah, what you do is like basically a shard over here accepts that some particular state over here is the state of that shard because someone basically publishes a bond that says, I agree to lose some amount of money if it's not true. And then individual contracts can get crypto-economic security bounds and then you can give an answer, and potentially this could all be done between like 2 to 3 blocks depending on how much risk people are willing to take. Now, the third alternative, by the way, is you can do an alternative execution engine, which basically kind of optimistically processes cross-contract calls with only 1 block of latency. And the idea is that in case there are any mistakes, there is a kind of slower gadget that runs a bit behind the main execution and cleans up the mistakes. And so if you're a client who's aware of a mistake, then you can kind of like locally predict what the execution engine will correct it to.
Right, this optimistic approach is quite nice. I mean, one of the reasons is that we have this spectrum of confirmation. So I guess it starts with a transaction being included in a block by a proposer, and then you have attestations piling on, and then you have more proposals which pile on, and then you have the beginnings of the formation of a crosslink with more and more signatures that come in, and then you have the crosslinks being included in the beacon chain, and then you have blocks building on the crosslinks, and then you have the FFG votes, and then you have finality. So there's this, maybe like hundreds of steps between no confirmation whatsoever and finality.
So one possible way to imagine these execution engines, like a very simple example, consider a UTXO system, where a transaction could just go on any shard and specify any UTXOs at once. And then the state of each shard is basically a list of UTXOs, where each UTXO also has a kind of a list of encumbrments. And encumbrments are like a list of UTXOs that have to be proven correct before that UTXO can be proven correct. And so you basically have this dependency graph that's kind of kept as part of the state of every shard. And then you have a delayed execution engine that gets executed, like basically 1 or 2 crosslinks behind that keeps on trying to say, yep, this UTXO is legit. Nope, this UTXO is not legit. And then it keeps on propagating upward, going through all the different dependency links over time.
I mean, in terms of cross-shard communication infrastructure that we want, I mean, at the minimum, we'll have these crosslinks. If we do have a nice synchronous scheme that works for general cross-contract communication, that would be very nice. But maybe an intermediate goal might be synchronous, if transfers between shards. So that would provide full fungibility between ETH and the different shards.
Mm-hmm.
So how do you think it will be decided which account or which contract will belong to each shard? And is this affinity going to be permanent, or it could change?
So by default, think of shards as just being universes or being like cities, and when you build something, you choose what city you build it in, right? So now there is such a thing as cross-shard yanking. So this is basically a generalization of kind of like atomic transaction locking techniques that I came up with that works for kind of solving trade and hotel problems. So the idea with the yanking is basically that imagine you have one contract over here, which is for booking trains, and one contract over here, which is for booking hotels. And you want to book the train and the hotel atomically because like there's no point in booking the train if the hotels are all sold out and vice versa. So you can do it in a purely asynchronous setup, but it's kind of like fairly inefficient. So what you do instead is you basically, step one, you send a transaction, and what this transaction does is, first of all, it reserves it splits up the train booking contract into two contracts. So one is the kind of train booking train slot contract factory, and another is a train booking slot. So now you have a train slot contract which represents the ability to book one particular train ticket. Then what you do is you send a transaction that basically says, I want to yank this train ticket, this contract to this shard. So what you do is you do the same dance that you did over here. Step one, you basically basically consume it on this contract. Then you can take the receipt, you can include it in over here. And then ta-da, you pop the train slot contract into existence. Then over here you have also a hotel slot contract, which is already on the shard. So now these two are on the same shard, and so you can basically atomically do, step one book, step two book, and if either of them fail, then revert everything. And so you book the two atomically. And then if you want, you can move the train slot contract back to the other shard. Though, in a lot of cases, there's not necessarily a need for these kind of individual unit contracts to have a particular home shard. They can kind of be yanked to wherever people want to yank them. Yes?
To be clear,
There's no native load balancing. This is like economic load balancing. Where
Correct.
You would go seek lower gas prices at the cost of maybe being a little more isolated and hopefully have a balance emerge.
Yes.
Again, I preface this that I'm still a beginner. What cryptoeconomic incentive or guard is there against someone somehow figuring out, I'm owning all the addresses on one chain and then kind of holding it hostage? I just want to know what...
When you say all the addresses, you mean all the notaries on one shard?
Yeah.
First of all, obviously, in most kind of standard security models, that's difficult to do unless you actually have like more than 40% or whatever of the total stake. But suppose either you do, or suppose that we're operating in some model where you can hack like whatever specific person you want, or you can bribe whatever specific person you want. That's fine. Like basically, what happens then is that this basically gets the crosslink, in the first version, right? The crosslink will get included, and basically as soon as this gets discovered by the rest of the chain, whatever portion of the beacon chain is including and after that crosslink would have to be discarded. In later versions, we do have things like fraud proofs and data availability proofs, which basically allow you to do a bunch of proxy checks for validity of the shard chain, where if anything here is invalid, then potentially you would be able to detect that even if 70% of the stake or even 90% of the stake on one shard is saying that it is valid.
Okay, the last one is exactly what I was wondering about. Thanks.
Yeah. In the short-term future, that would probably be the erasure-coded data availability stuff and fraud proofs. In the long term, you would basically have Starks, and you don't even need any kind of interactive magic. You just this is the long-term utopia. You would just have a Stark over here that basically says, here is the data Stark. This is valid, and the entire history is valid, and this is a pointer to all of the data in this chain and all of its recent history, and the data is erasure-coded, and you can randomly sample it to verify that it's available. And so any clients can basically download a couple of megabytes of data and verify that an entire shard has the validity and availability properties that you want. But that's Ethereum 3.0 vision, and we're more than a decade away from it.
Still still on crosslinks with calls. If we add hits to the problems, for example, do I need to have an account on both shards? How does it going to work related to Ether? Ethers. I mean, do I need to have Ethers on 2 shards or not?
So if you want, like, so first of all, what you would realistically do, right, is when you make your first transaction here, along with this call, you would include some amount of Ether, and then that amount of Ether would basically be available for spending when you need to consume the receipt on this shard. So, yeah. Now, I mean, this is kind of imperfect because you would realistically have to overpay a bit to make sure that you can pay whatever the gas price is. But like outside of that, and there are like ideas on how to improve it in the future, but that would like add complexity, and it's a later stage thing.
So by default, the remaining part will be on the second shard. If I start with 0 on the shard 2 and I call it from shard 1, I will send more Ether than necessary, so the remaining will be on the call shard. Okay.
It's probably also worth noting that realistically there'll be like payment channel and lightning networks floating around on top of this as well. So you could, like if you need a top up of Ether at some particular points, then you can basically just like use some decentralized shard for shard exchange and just like swap it.
So I'm perfectly clear, this design doesn't support like quadratic sharding, but it's not necessary.
This is quadratic sharding.
Oh, it is? Or?
C over 2, I almost drew C squared over 2, but it didn't. But yeah, it is quadratic.
Okay.
But this is definitely not super quadratic.
Right.
Yeah. And I mean, like, I think I might have said this on the internet, but like, so I think we can, like, the Ethereum chain could survive in the long term without super quadratic sharding. And the reason is that, like, first of all, especially with the efficiency gains that we get from signature aggregation, like even that by itself, right, 4,096 shards multiplied by, you know, like each shard doing, say, 5 to 10 transactions per second, that already gets you to, you know, like 40,000 transactions a second. And with Moore's law, this every time the capacity of a computer plus the efficiency of the software doubles, the capacity of the system increases by a factor of 4 up to some point. Now, with Ethereum 3.0, where like everything is starked on top of everything else, then making it exponential does become easier. But like there are dangers to going exponentially even in that case. Basically, because you're creating a dependency that a larger set of nodes would be online.
Cool, thanks.
What is going to happen to the current main chain? It will just die at some point, or?
This is a question mark. One idea I have is that, like, basically the main chain will continue existing for a while, and then eventually it can either become a side chain of the sharded system, or I mean, basically you can have a smart contract. The main chain become a smart contract on some sharded system. Or basically one of those two possibilities, right? Or the main chain could become some fancy ZK snark plasma chain on top of the layer 2 system. So basically, it should be possible to set it up so that the main chain, with its logic, kind of continues existing forever, but it doesn't add consensus complexity to the new layer 2. Really, which is, I think, something that we do want to go for. Like, we don't want to sort of grandfather in the EVM into the Ethereum 2.0, so we have to deal with two virtual machines forever. But fortunately, WASM is fast enough that you can just do EVM inside of WASM.
So at the point where we have the beacon chain and people start depositing, and we have these cross-references to the legacy chain, the current one, Does that imply that the legacy chain will have finality and we will reduce
Yes.
the rewards already?
Yes.
Okay.
Yeah, I mean, the legacy chain, yeah, you will get indirect finality because the beacon chain points to the legacy chain, and so the beacon chain carries finality, so it would implicitly finalize the legacy chain, and that is, it is a for-choice rule that clients can definitely kind of decide to listen to.
All right.
And like, it definitely, it definitely does make sense, I think, to reduce proof of work rewards, especially when, and like more and more as the stages progress. Like basically because if, at the point where like 80% of users have migrated to the layer 2 system, there's no point in paying even half an ether a block on the proof of work.
Follow up, unrelated. I think at one point it was mentioned that shards could basically develop in different speed. Like one shard could, kind of change the rules already. Is this still like covered in this design, or?
So this design is homogeneous sharding, and I mean, like, I personally am in favor of homogeneous sharding and not this vision of like individual shards being experimentation zones, basically because once you start going in that direction, it starts massively bloating consensus complexity, and like I think like something like a plasma chain or a side chain is probably the more appropriate zone, kind of experimentation ground.
When's the next difficulty bomb?
It's like, I think when we calculated it was something like the first half of next year.
Oh, okay. Cool.
We should check to see if the difficulty is going up. Now I know that the difficulty has been stalling at 3 trillion lately, but then there are also Bitmain's ASICs to look forward to.
So maybe that's a good time to reduce the mining reward?
Possibly. Let's see, network difficulty 3390. Wow, it's been staying at this 3000 level for a very long. It's been like flatlining, like basically flatlining for a very long time.
Does anyone have a Bitmain ETH miner yet?
T1 exahash and beyond. No, right now we're at like 3.5 petahashes, for difficulty, and for like hash rate we're at like a quarter petahash, I think.
And to go back to the idea of experimentation, I still think there is an opportunity to experiment at the application layer. So you can totally write your own execution engine that for a specific shard at the application layer. So, I mentioned the TrueBit thing, but you could, for example, have try and build the equivalent of Zcash on one.
Yeah, no, so like one thing that you can do, right, is you can come up with your own separate meta protocol that basically says any transaction to be part of my meta protocol has to tag itself, and like tagging just means, the first 5 bytes equals some particular value. And then you can have a Zgate Snark or a TrueBit engine, whatever, that basically says, oh, like here we have some gadget that basically that can eventually interactively somehow calculate the result of processing all of the transactions in the blockchain that have that particular tag sequentially. And you could even have, stick Ether into the smart contract, and so then the execution engine could kind of indirectly control Ether.
And so how we potentially can foster this kind of experimentation at the application layer is by distinguishing between raw data, which we call blobs, and transactions, which are blobs that entered in EVM. And when you think of EVM 1.0 right now, you have a minimum gas of 21,000, even if you were to put like a 1 byte thing. And so I think there's an opportunity to have a way to completely bypass the EVM so that you only pay for the data, and that will make it very cheap for these alternative execution engines to kick in.
For the rewarding part, in the past, for sharding, the plan was to have around 1% of inflation, if I remember correctly. Rewarding, the rewards.
So in the past, for sharding, the plan was to have 1% of inflation.
Like rewards are still an unsettled issue, and I know like I have my views, Vlad has his views, and like people like not determined yet. But like I definitely think that we can do. I'm very confident that we can make do with less than 1 million ETH a year in rewards, and like it's very possible that we can make do with 0. For reference, I think transaction fees by themselves are already doing about 500 Ether a day, which is something like 180,000 Ether a year, right? So if we can dare say that proof of stake will be 30 times more efficient than proof of work, then like that's enough to cover it.
So in terms of kind of the micro rewards and penalties for the sharding scheme, so every validator will have n+1 balances, where n is the number of shards. So 1 in the beacon chain and then 1 for each shard. One of the things that we'll have is all the penalties will be aggregated in the beacon chain. And the reason is that if your balance becomes too low as a validator, your deposit becomes too low, then we want to force ejection so that you can't cheat the system. And so in the shards, there will only be rewards. So there'll be rewards from the transaction fees, but there will also be rewards for participating as a proposer.
So I think that I didn't fully get, or actually there are a lot of things that I don't fully get because I'm fairly new to this. But this proof of custody thing, so as far as I understand, you give out this proof that you have some kind of data, and if it later it is revealed that you don't, then you lose some sort of deposit. So are there valid cases where you are losing this data because, I don't know, your database is ruined or whatever, and is this just a case if shit happens, or?
Yeah, so this is the sort of stuff that would get covered by the partial slashing mechanism. So the idea basically is that if you're the only one in some committee who screwed up, then your penalty would be lower, but if you screw up at the same time as many other people screw up, then that's more likely to be an attack, and so you get penalized much more.
I mean, one thing to mention is that it's a proof of custody at the time of signing, is not a proof of storage that you will have it in the future. So if you had the data at the point of signing and you did make the right proof of custody, then it's quite likely that no one will challenge you because it would be a waste of their money to challenge you.
Though it is worth noting that from this set, it is possible to recover the original data set. And so in order to carry the data needed to respond to challenges, you have to store the original data.
Right. So if there is some sort of a doubt as to whether a piece of data is available or not, then there is this retrievability mechanism and challenge mechanism. Even if you have the right bit, you can still be challenged. So better, keep the data.
And this doesn't obviously cover like malicious provers that decide to delete one particular bit of data and all coordinate on deleting the same bit. Though, I mean, like if it really wants to, we could probably like battle that with erasure codes, but like that's later stage. Yes.
So I'm wondering if you could talk for a second about what synchrony assumptions are required for the BLS signature aggregation part of the protocol, and how that relates to, I guess, targeted censorship. And have you analyzed that at all?
Sure. So first of all, like the fact that the signatures are BLS aggregated does not, like from a network, from a perspective of like the pattern in which things move through the network, it's exactly the same as it would be if the blocks were just bigger and contains a pile of the signatures. Like the BLS aggregation in this case is not a multi-step procedure. It's just taking signatures and then literally adding them together. So, like basically what it looks like is, well, this kind of graph where between two blocks, like basically one block gets published, and within that time, a bunch of people would need to assign signatures, and the block would need, and a block could include those signatures. So if you want the chain to kind of run smoothly, you basically want this time to be bigger than twice the network delay that's expected to be the case in most circumstances. And if network delay ends up temporarily going above that, then, I mean, obviously the chain could stall, though the underlying Casper FFG mechanism does provide safety, so like it can't get reorged arbitrarily. And in general, like Casper guarantees safety under asynchrony, but not liveness under asynchrony, because that's how like BFT algorithms of that entire category work. Were you looking at, did that answer your question, or were you looking at like other network issues?
So I was wondering, like, how many signatures are required on, let's say, a certain block to receive the protocol?
Right, like probably a few hundred.
Is there like a constant threshold, or?
It is you definitely can calculate the maximum, right? So the maximum is basically the maximum theoretical possible number of validators divided by the length of an epoch. So if you want to calculate it, that would basically be 4 million divided by 100, which gives 40,000, and 40,000 signatures times like the obvious 64 bytes basically gives a couple of megabytes.
But is there any incentive to go like past the minimum threshold?
What do you mean by past the minimum?
Like how many signatures you actually need on a block for the protocol to proceed?
Yeah, so this basically depends on the total number of validators participating, right? So like if literally everyone is staking, then at least with the current numbers, it would work out to 40,000. If 10% of people are staking, it would work out to 4,000. Though, you know, like it is also worth keeping in mind that like you could potentially have sort of multiple tiers of aggregation, right? Where like one node basically passes along a signature that says I contain these entire 500, like all of the indices I know about in this subset. So you can like basically if you like, it is possible to create second layer network protocols that kind of shard the aggregation process at the P2P layer, and then you can knock down each node's bandwidth requirements to like a square root at the expense of an extra round of people talking to each other. And like, yes, obviously, if during the test nets we decide that like doing all of this in 5 or 6 seconds is remotely dangerous, then we'll push that up.
The stack is 32 meters, as far as I know. Why 42? Why 10?
We like powers of 2. Yeah. Yeah, like that's basically it. You know, we'll probably change the epoch length to 128 at some point as well.
Everything must be a power of 2.
So did you know that in the original spec for Ethereum, 1 ether wasn't 10 to the 18 way, it was 2 to the 60?
So much better.
Yeah, Randall and VDF, a few words about differences between those things.
Okay, so basically Randall allows the possibility for abort. So at every height, you have a proposer who needs to reveal his next Randall commitment, and because he knows what he's about to reveal, he basically has 1 bit of attack surface at this particular point in time. But it turns out that because of the recursive nature of the construction, where the randomness right now will influence the randomness in the future, an attacker can basically strategically abort in order to have more participation in the chain in the future, which kind of gives them an edge versus the optimal kind of 50% threshold that we'd like. Another kind of thing with Randall, which I don't like too much, is that we would probably need the shards to closely listen to what is being revealed at the beacon chain layer. So, for example, if one of the proposers at the beacon chain decides to abort, then the whole sharding system freezes for 5 seconds, which is obviously undesirable. So on the other hand, the new construction is basically where you have 2 steps. And the metaphor that I use is the sponge metaphor. So you have a sponge which is initially dry, and then with Randall, you add entropy into this kind of entropy pool, and the sponge kind of absorbs all the entropy. That happens in one of the epochs. And then you use all this entropy as a seed for your verifiable delay function, and then the verifiable delay function will basically squeeze all the entropy over time in such a way that you can't predict what the entropy, what the random numbers generated on the other side will be. And one of the properties of this VDF construction is that you have a very stable beacon. So there's no possibility for abort, which is very nice. Another thing that it kind of allows us to do is to, as I said, kind of more closely decouple the shards from the beacon chain a bit more. So if the beacon chain, for example, forks, we don't want to have to recompute all the committees and basically have all the shards also revert. We want to have the shards be as stable as possible, even with the beacon chain forking.
So this is my kind of chart of the 3 major mechanisms for getting data into, getting entropy into a proof of stake chain with their various kind of weaknesses. So Randall is basically kind of like feeding in randomness by having participants provide hash pre-images of data they already committed to. A VDF basically has people submit commitments, and then later on anyone can calculate VFC, but calculating VFC takes some amount of time. And then there's like various kind of like collaborative like committee threshold schemes that use some fancy procedure where at the end of the procedure you have a scenario where, like, let's say any 50 of a group of 100 people can reveal the data, and whatever 50 it is, they'll end up revealing the same data. So in terms of the manipulation properties on the Randall side, like basically you can manipulate the randomness by 1 bit by choosing to forgo your reward. On the VDF side, if you have an attacker that has an ASIC which is fast enough to basically calculate VFC so quickly that he knows the answer of VFC before he has to make the decision about whether or not to submit C, then he can break it. Though I will say that our particular way of using the VDF, like basically if you use a VDF well, you can design a system where even if this happens, it degrades to just being a Randall. So the other direction a super ASIC attacker could do is you could basically get the system used to a high level of difficulty and then suddenly disappear. And if the super ASIC attacker has a very high advantage, then the rest of the network will just like greatly slow down for some time until it adjusts. And then for the n over 2 of n, you can't really manipulate it unless you have half, but it has other issues. One of them is that it can't survive more than 50% going offline. And the other is that it requires like complex distributed key generation setups, and it depends on public key cryptography. So like out of these, I guess like I personally, I mean at this point I am writing this kind of VDF with a backstop where if the VDF gets broken by an async, then it degrades to being a round out.
So I think that's the end. Yeah. Thanks.